Well, thank you. I'm Ken Wardley, the FOTEC chair, and I want to welcome you all to a Fiber Optic Sensing Association webinar. This week it's monitoring of large concrete structures, presented by Professor Dr. Werner Lienhart. Next slide, please. Just a real quick, for those of you who are new to FOSA, what FOSA is, we are a nonprofit association. We were formed in 2017 in DC. And we're really promoting fiber optic sensing across many markets and providing education on benefits of DFOS through technology awareness, advancing public policy, and promotion of DFOS. So membership is open globally to people who make, install, support, and use distributed or quasi-distributed. So as a commercial, I'll say any book members or people who are not members or would like to join, please reach out to us. We're always looking for members. And hands-on activities all the time. So then just next slide, this is just a list of our current members. Just to note, we do have consultant members as well, so we do have a couple tiers available. So thank you all for joining, and hopefully you find this useful and maybe become a member. And I'll turn it over to Mark Unkefer.
Thank you very much. I'm Mark Unkefer, and I'm the Executive Director, and we're really pleased to have this. Is a little different than our normal webinar in that it is the product of our Technology Committee, which is really one of our flagship activities as an association, as opposed to the product of a specific company. And it reflects work that they, as a committee, have been producing for a while. This particular webinar is presented by Dr. Werner Lienhart, who is a professor at Graz University of Technology in Austria. And it is an example of the great cooperation that FOSA has been able to have with academic institutions. So Werner, we look forward to your presentation.
Thank you very much, Kent. Thank you very much, Mark. And welcome to today's webinar. So today we're going to talk about monitoring of large concrete structures. And what we, the technical committee, would like to get across today is that the benefits of fiber optic sensing for structural health monitoring of large concrete structures. So we're going to take a look at sensing possibilities. We're also going to take a look at how you actually install or embed a fiber into a concrete structure, or how you apply a fiber to existing concrete structure on the surface. We have prepared some application examples for you where you can see the real-world performance of distributed fiber optic sensing for concrete structures. And finally, we're going to take a look on the overall benefits that fiber optic sensing can bring in the monitoring of large concrete structures. When we take a look first on SHM, so structural health monitoring of large concrete structures, this can have various reasons, and this can also stretch over the whole lifetime of a structure. So SHM can already start at the design phase of the structure. So here you may want to use monitoring to see if your design assumptions are appropriate. So let's assume you have a high-rise building that needs solid foundations. One question could be, is the design length of your foundation piles appropriate? If the piles are too long, you just wasted money. If the piles are too short, you may not provide stable foundation for your structure. As soon as the construction starts, SHM can be beneficial to assess the quality of the construction process. So for instance, was the jet grouting procedure performed correctly, or were there some issues with the quality? However, SHM is not just a passive process. Monitoring data can be directly be used to adapt the construction process. Due to the measured deformations, you can change the excavation length in tunnel construction, or you can also control the tensioning step in pre-tensioning of concrete decks. When the structure is already there, monitoring is useful to detect structural deterioration at an early stage. And here the goal is really to detect it at an early stage, because maintenance work and repair is usually much cheaper at an early stage of a problem than later on. Since we're talking about concrete structures, one of the main questions there is when and where do cracks occur? And finally, of course, all of us want to avoid the failure of structure, and SHM plays a vital role in early warning systems. So these elements are maybe true for different types of structures. However, concrete structures, especially when they are large, have specific challenges. So first of all, they usually have a very long decisive lifetime. So we're talking about 100 years plus. So everything that you install for monitoring should also work 100 years plus. And can you actually guarantee that? Secondly, interesting with monitoring of concrete structures is that we do have some areas where we already know problems may occur. So usually those are bearings or joints. However, we also have defects that can occur at any location along the structure. So this means we have on one side focus areas, but on the other side, we also have to monitor the complete structure. The third topic is that we are currently building exciting new structures that have to be monitored. However, we must not forget about our existing infrastructure. And especially with concrete structures in Central Europe, we have major issues with aging bridges, aging water dams, and aging tunnels. So we need monitoring solutions that can also be applied to existing structures. And finally, we have harsh environment. And this is also two-folded. So on one hand, our structures are usually placed at a remote location within a harsh environment. So here all the sensors do have to work in that harsh environment. And on the other hand, the construction process itself may be harsh. So the sensors also have to be robust enough in order to survive any installation work. And now we're going to take a look on how we can deal with these challenges with distributed fiber optic sensing. I'm pretty sure many of the attendees know about fiber optic sensing. So just a short recap, what is different compared to telecommunication? So in telecommunication, the goal is to transmit data from one end to another end. So basically on one side, we have a transmitter, on the other side is the receiver. In sensing, we're actually working with the backscattered signal. And when we're talking about distributed fiber optic sensing, we have a sensing line without any gaps. So we get at any location information of the current status of the fiber. And depending on now the technology which is being used, it could be a chain of thousands of strain sensors. So distributed strain sensing, DSS, thousands of temperature sensors. So distributed temperature sensing, TTS, or acoustic sensing, DAS. One important aspect is we're working with glass fibers. So the core of the fibers is in many cases exactly the same in sensing as it is in telecommunication. However, when we talk about strain sensing, we usually need a different cable. Here you see a sketch or some pictures of the setup of a telecommunication cable and a sensing cable. So within a telecommunication cable, the goal is that the signal is more or less unaffected by everything that happens on the surrounding. And this is usually reached by allowing differential movements. So one setup would be like shown here, that you have gel-filled tubes where the fiber can slide between the outer surface and the fiber core. Differential movement is allowed. On the other hand, when we talk about sensing, we have the completely opposite goal. We want that our fiber core experiences everything that happens in the surrounding of the cable. And this means you need a totally different cable layout. So in this case, the fiber core has to be rigidly connected to all layers of the cable so that any deformation on the surface of the cable is fully transferred to the core of the fiber. Although, as again, the fiber may be the same, the setup is different. And now it depends on the application, what is the right cable to be used. It could be a tight buffered cable, where you just have a thicker buffer that is tightly coupled to the cable. When you need more robust cables, it could be a fiber metal tube, a FIMT. So in this case, we have a glass fiber that is either along the entire length glued to a metal tube or clamped in certain distances to that metal tube. If it has to be even more robust, you can use special sensing cables which have strengthening members inside and special structures on the surface. And here the challenge is to find the right optimum, having a robust enough cable to survive the installation, but also the thicker and more robust the cable is, the less sensitive the cable is. So here you have to select the right cable for your type of application. Regarding ordering that cable, it's like with telecommunication cable. You order the cable on drums, a few hundred meters, kilometers, and then you just cut off the length that you need and splice the connectors to the cable, and then you have your final cable that is ready to be installed on site. Regarding signals, we're working with backscattering, and I'm pretty sure most of you have seen this graph in the different variants somewhere else already. What's important now for concrete structures, we may use all different backscattering signals. It's just a question what our focus is on. When we're interested in vibrations, we use DAS, and DAS basically relies on radar backscattering. However, also high resolution distributed strain sensing also uses radar backscattering. When we talk about strain sensing over longer distances, usually Broglie backscattering is used. So Broglie backscattering shows a shift in the Broglie frequency depending on temperature and strain. And the cross dependency already causes an issue. So when we're interested in strain, we also have to take care to capture the temperature, usually done by running two cables in parallel, one optimized for strain, one optimized for temperature. And by taking the reading of the temperature cable, we can compensate the temperature effect on the strain cable. So temperature we always have to take into account, although we are maybe just be interested in strain itself. However, we could also use Broglie sensing to temperature sensing if you're just interested in temperature. Another way for temperature sensing is to use the Raman backscattering signal. So really depending now what your main focus is, instruments measuring relay, Raman backscattering are the right choice. Just to give you a bit more idea of what is possible with distributed fiber optic sensing on large concrete structures, we're going to take a look on some application examples. And the first one is about pile load testing. So this is a usual test which is being performed either to assess the right pile length or to assess the right construction method of the pile. A pile is being constructed and then vertically loaded. So in this case, we see a setup where load is applied vertically on top of the pile. This induces a length change, and due to the distributed nature of strain sensing, we can then measure the strain distribution along the whole length of the pile. So our force is in this case in the same direction as our fiber optic measurement line. Also important to notice, very often those fibers that are there mainly for load testing, of course, stay within the structure, which means they can also be used for the long-term monitoring when we want to see what happens to the foundations of the structure in the long term. You can see a usual setup where fibers are installed along different lines, and let's just select one line and see what's happening when we apply vertical load. We do see here a strain profile, and by closer looking we can identify we have decreasing strain with increasing depth. And the inclination of this slope gives us information about the shaft friction. So this is an important indicator about how well the pile interacts with the surrounding soil. However, so far we just look at longitudinal changes. But with fiber optic sensing, we can also measure deformations orthogonal to the sensitive axis. So if we do have a reinforcement cage like here and apply fibers in two different lines which are separated by certain spacing, we can also measure and identify deformations orthogonal to the sensitive axis of the fiber. So imagine we have here a beam with a certain length and install fibers at a certain distance. When load is applied, we do see then shortening, so negative strain on one side of the neutral axis and positive strain on the other side of the neutral axis. And by taking the differential strain readings into account and dividing it by the distance of the strain cables, we can determine the curvature at this location. So at every location, we do get now the current curvature, and by double integration, we can also derive the deflection curve at this of this element. And this concept is used in various applications. I want to show you one example here. So here, this is an example where a 70 meters deep vertical shaft has been produced. So we can see here the 30-meter diameter of this shaft. And the question was, how do the walls of the shaft deform during the construction process? We can see here the layout. We had different diaphragm walls. And when you make excavation, you have here the load disappears, and then the wall can actually bend inside to the shaft. And this bending can be measured by having a fiber optic cable close to the soil and close to the shaft. Just as seen before, now we have the load coming from this side. We have here two fiber lines, and by taking a look at the differential strain, we can determine the curvature. And again, in this case, also strain cables and temperature cables have been installed. Temperature cables, on one hand, for compensation on the strain reading, but also on the other hand, temperature may be a valuable information by itself. So what's the result? What we're going to see here now is not strain anymore, it's already the derived curvature. We see different construction steps. So for instance, here excavation takes place from 35 meters down to about 48 meters, and then we move further down. We can see two colored lines. These correspond to different panels. So one is panel 15 and the other one is panel 20. We can see when this excavation step takes place, almost no curvature change. However, when we come to closer to the chalk area, we do see that suddenly curvature occurs. And this is an important information, especially when you want to calibrate your numerical models. What we can also see here in the black curve, this is the numerical simulation result of Plaxis. And what you can see, it's a much smoother curve. And this means that maybe the stiffness of the soil was not assessed correctly. Maybe it was assessed too soft. So therefore, the strain can stretch out over a larger area, causing not such a large curvature reading. So by taking these readings into account, we can actually calibrate and verify our numerical models. So far, we've talked about longitudinal strain and measurements where the load comes orthogonal to the sensitive axis. Interesting is that temperature can also be used for several applications. And one application is the thermal integrity testing. So this is another pilot example, different location, but here we're going to do both things at the same time. We're going to take a look at the temperature readings, but also then on loading tests. When I think about temperature, temperature also indicates curing processes of the concrete. And here the idea is, the thicker the concrete, the longer it takes in the curing, meaning that you have a peak in temperature which degrades slower than when you have a thinner thickness of the pile. So by just taking the temperature reading or observe the changes of the temperature reading over time, it's possible to predict the thickness of the pile in various depths. And by doing so, you can assess the performance quality, so how well and how homogeneous that pile was actually being produced. And with the same instrument, just taking a look at the different effects, and when we're taking a look at the strain readings, we also can see deformation. So in this case, it is again a load test, but load was not applied from the top. Load was applied from the bottom here in an Osterberg cell. And we see now again the strain profile due to different load. In this case, we have a rather flat area at the beginning, and then it's rather increasing rapidly. So here we can see the load distribution, and this B can be then converted into the friction. So we again get information about the interaction of the soil and the pile and know how much stability our pile will give us for the foundations in this case. Temperature, in this case, is used to derive pile shape. Of course, temperature can also be used for fire detection. And here we do see one example of a railway station at an airport. So you can see here the concrete area with the platform of a railway station. and also the roof of the airport. And in this case, there are different applications. So with one sensing line, the engine room is served, a section with cable ducts, the glass roof, another section, and again, a room. So we can, with one single line, observe different areas with different focuses. In the cable ducts, we're taking a look if fire is caused maybe due to some electricity problem of the cables. And here, in order to make it more robust, two cables are guided through. So in case one breaks, we can still measure from the other side or use the other cable. What you can also see here is the car park in order to detect fire of cars in the car park. One could argue fire detection in such locations and also in tunnels is also possible with cameras. Of course, that is true. However, what we do know from tunneling monitoring is that cameras are not really well suited to identify the location of a fire. So first of all, they are usually stretched over larger distances. And secondly, as soon as the fire starts, you also have smoke developing. And pretty soon you cannot see anything on the cameras but just smoke. And in this case, fiber optic sensing can still identify where the fire location is, and you can steer then the fire brigade to the right spot. So this was now some applications, but actually, how do you get your fiber on or within a concrete structure? There are different options for doing so. So when we take a look at embedding it within the structure, we can on one side directly embed fibers into the reinforcement bars. This is what you see here. The groove has been made and a cable or fiber is placed into the reinforcement bar with some glue. We can also mount the cable on top of the rebar. So in this case, it's continuously glued to the rebar. Another option would be to tie it with cable ties to the rebar. But the important thing is here that the rigid connection is not really made by the cable ties. The cable ties are just there to hold the cables in place during the pouring process of the concrete. Afterwards, the connection is made along the whole length by an interaction of the concrete with the structure of the cable. So here we have cable ties at a certain distances, but in between we have this structured cable, and this cable basically interlocks with the concrete. So this cable has a similar structure as the rebars, and also with the rebars, the idea is that the concrete interlocks with the rebar, and also in this case with the cable. Of course, using clamps is also possible, but what we can see here on the right-hand side, so here we do have clamps and the fiber stretched between these clamps. So this is everything that is possible to during the construction of a concrete structure. As I said already before, unfortunately, we also have to deal with problems of aging infrastructure. So we have to attach our monitoring system to already existing concrete elements. And there are also several ways doing so. One way is to attach it continuously along the whole length, but using some adhesive and mounting it in this way to the concrete surface. Another way is when you know exactly where to look at, for instance, like joints, that you make an anchoring on one side of the joint and an anchoring of the other side of the joint, and then you actually measure length changes of this joint. And we are now going to take a closer look on this second example, where we do see how such an application can look like in real life. And this is now the monitoring of a water dam. And personally, I find this application really interesting because it comes from the fact that we have an old aging structure, but then suddenly we change the loading regime of the structure. So when you talk about large water dams in mountainous areas, usually they were made for storage operation. So this means when the snow melt starts, you're starting filling up the reservoir until autumn, and then you produce energy over the winter. So we have one slow yearly cycle. However, nowadays, the power plant is being changed. So instead of just using storage operation, it's being updated for pump storage operation. And pump storage operation means we do have the main reservoir and the second smaller reservoir. So here we store water, and when there's too much energy in the energy network, in the electricity network, we use this extra energy and pump the water back up to the main reservoir. So although we keep the water dam the way it was, due to the change of the operation, we have a completely different loading cycle. So now it's not just one slow yearly loading cycle. We pump up the water several times per day, and this also will yield to a different impact on the structure. And the question is now, how does this old aging structure react to the new operation type? What we can see at the bottom here is that such a massive concrete structure was not produced in one single block. So we can see here we do have vertical joints. And when temperature changes, the distance or the size of the joints changes, but also when you increase or lower the reservoir level, the distance between the joints also changes. And now the question is, how can you observe these tiny movements that occur when you just change the water level a little bit? So you can access the joints from the inside of the water dam. So usually there are maintenance corridors at different levels. We can see on the left-hand side one of these corridors. The joint size is usually measured a few times per year manually. You can also see how joints look like after several decades. And here a manual dial gauge is used, and depending on the operator, you reach a precision, let's say, of about a few hundredths of a millimeter. In order to see what's really happening in pump storage operation, it's also possible to use fiber optic sensors. So we have fiber optic cable installed, and at every joint it's connected right and left of the joint, and in between it's stretched. And what we can see now is how the joint or the water dam in total reacts to small changes. On the right hand side, you can see the observation time of about 2 weeks. In the first week, the water level is almost constant. And then we do see a small but steady increase of the water. When you take a look at the size, so it's increasing of about 8 to 9 meters. You can also see the temperature is varying during that observation time. So we go down to, let's say, -8, 9 degrees, going up to about +10 degrees. And in the center, we can see the reaction of different joints. So some joints show only very small movement, some joints show a larger movement. This is now depending on where they are within the water dam. We can identify the reaction to the water level change. So if the water level rises, the joints start to close, and we can also see the daily variations. So here there's an overlay of water level increase and daily variations. On this side, it's mainly daily variations. And what you can also see is the amplitudes of the daily variations are just a few micrometers. So even if you would have an operator there standing all day long making manual measurements, all of this would be hidden in the measurement noise. So 200ths of a millimeter would be basically down here. So everything that happens until here would not be visible. Also, you would not be able to detect a small water level change. So due to the high sensitivity, we can really detect very small movements which may not be possible with other techniques. As initially said, one important point in concrete monitoring are cracks. So let us take a look now, what is a crack and how does a crack look like in a strain signal? Strain is basically a length change divided by a base length. So if we don't have any cracks, so if we have an intact structure, we do have zero strain along the whole structure. If a crack occurs, we suddenly have a length change. So suddenly we have a length change, which is the length of the crack. However, we divide it by the initial length, and the initial length is 0. And this means theoretically, if we have a crack, we should get a strain reading, a strain peak that goes up to infinity. However, due to the pulse length of the instrument, due to the cable layout, it won't be a peak going up to infinity, but it will still be a definitely identifiable strain peak. So we see like a strain peak could look like, so we have measurement noise, then we have going up a maximum and going down again. And the size of this peak and also the width of this peak depends on obviously on the crack width, but also on the spatial resolution of the instrument, of the used cable, and if the cable has been applied on the surface on the used adhesive. But the main point is, by reading the strain signal, we can tell when and where a crack occurs. And I want to show you this on an example, not on a simple straight beam, but on a curved beam. And this is actually a tunnel lining segment. So this concrete element is about 6 meters long, and many of these segments form then a ring that a tunnel boring machine places to form the tunnel lining. So in this case, it's a load testing frame that can apply vertical and horizontal load. And for this presentation, we are going to take a look on vertical load. So when we apply vertical load, we expect negative strain along this line, so shortening on the top, and positive strain, so elongation at the bottom. And in order to explain the results in more detail, in this case, we have placed several fiber optic lines in this tunnel lining segment. So we're going to take a look at 3 lines where we have always signals on the top and at the bottom. And then we also do see here the load regime. So load has been increased, decreased, increased, decreased, and finally increased again. What we're going to expect is that we will see shortening of the blue line and elongation of the red line. And the question is, do cracks occur when we apply that load? So let us see what's happening when we just put now vertical load on that lining segment. We see what we expect: positive strain at the bottom side and shortening negative strain on the top side. Similar behavior of all 3 lines. We increase the load and suddenly we see those peaks appearing. So we see that in line 2 and 1, cracks already occur. Now cracks also occur on line 3. The scaling changes here because we also have an increase of the crack size. So we can see when cracks occur, we can see how they increase. We can also see that the area that has been affected by cracks is getting larger and larger. We're going further up, and then we can also see how reproducible that result is. So we go up and up, go then back down again, and then we're going to see if we reach the same signals when we're going up again. So we're going down. So you can see almost the whole beam is already showing cracks, and then basically going up again. So by taking a look at strain signals, we can identify where and when problems do occur. This is being used as quality assessment of the tunnel lining segment. So if they are working according to the specifications, and for tunneling, usually you also have different lining segments depending on how strong the tunnel lining has to be. So you can also verify how different segments with different reinforcement cages and different concrete react to vertical load. And this works not just in load tests, this also works in a real tunnel. So in this case, we do see a tunnel boring machine, and this machine places within its shield a ring of those segments. So usually it's about 6 to 8 segments, and these segments form a ring. And the nice thing here is that the fibers have already been applied in the factory where the tunnel segments are being produced. So after the tunnel boring machine places those elements, the only thing that has to be done is to connect one segment to another and connect them to a communication line. And you can also connect them several rings. And with one single instrument, you can control several rings. And this instrument can be also in a cross passage or even outside of the tunnel. And what's also nice is you can also measure what's happening underneath here. So this is an area which is usually very different difficult to be observed, so you cannot access that with laser scanners or cameras. So fiber optics may be the only way to really measure distributed what's happening underneath here. Another example just to show how data can be visualized. So this is now again a tunnel, but this is for water transport, and in this case 4 fibers were installed. And in order to see what's happening, it's also very useful to use water plot diagrams. So water plot diagrams are commonly used in distributed acoustic sensing, but can also be a valuable tool to visualize areas which have problems and how problems evolve over time in strain readings. So what we do see here, and this is a tunnel in the area which is prone to earthquakes, we do see there was some effect happening, and due to the effect we can see 2 areas which show an increase of strain. So on this line here we see the time, here we see the location along the fiber. So this means everything that is blue or entirely blue, nothing is happening in this location. But then we can see this area where strain is increasing, and another second area where we also see strain is increasing over time. So we can now take a look at time curves. We can also send in repair troops and tell them exactly where to look at. So far, you've seen different applications. You have seen that we can take a look at longitudinal strain, we can take a look at bending, we can take a look at joint opening and closing, we can take a look at cracking. But one question that very often arises is, how robust is all of this? So first of all, in order to make it work in concrete, the cables have to survive the installation. And concrete environment can be rather harsh. And one of the harshest environment is shotcreting. So shotcreting means that you have a reinforcement grid, and on this grid, concrete is sprayed. And basically it's more or less shot, not just sprayed, and that's why you have the name shotcrete. And the cables that you have applied have to survive this process. And just to see what shotcreting means, take a look at this video. So with high pressure, concrete is being poured directly onto that cables, and the cables do have survived that installation. But when you select the right cable, those processes do not really harm the sensing cables. As I said initially, we're talking about 100 years plus. And there the question arises, how do you prove that the monitoring system works for 100 years plus when the technology is not around for 100 years plus? So of course you can apply accelerated aging tests, but personally what I can say is it definitely works for several decades. So I personally have installed fiber optic cables in this monolithic bridge more than 20 years ago, and these fibers still work. So we can still use the fibers integrated in this bridge for monitoring. Because from the theoretical point of view or conceptual point of view, fiber optic cables are meant for long-term monitoring. Because at the sensing location, you don't have any electric component. And also at the sensing location, there are no mechanical moving parts. So typically error sources of other sensors are not existing for fiber optic sensing cables. So just from the layout, fiber optic sensing is a very good technology for long-term monitoring. What sometimes is forgotten, that it's not just about how to make a successful installation. There are other things that are really crucial, and just want to say a few things coming from my own experience. So it's really important that you document where you have installed the fibers. So in this case, we see the 3D spatial location of fibers installed in a concrete lining. So in this case, there was also a laser scan being made, but the important thing is the blue line. So this is the routing of the fiber optic cables. It's important that this information is being passed on. So this information has to go into the databases, this information has to go into the CAD drawing, this information has to go into the BIM models, and also in case if there's a digital twin, this information has also been in the digital twin. Next thing is, it's not just important that this information is stored virtually somewhere, it has to be visible on site as well. So you have to make markings of the cable locations on site. And in order to have a successful monitoring project, everyone has to be informed that sensing cables are installed. Sounds pretty obvious, but this means everyone who is doing any work within the next 100 years, any drilling of a handrail, any drilling whatever, has to be informed that fiber optic sensing cables are installed there. And this can be really challenging. Just some examples where things didn't work out perfectly. We can see here the very complex formwork of a bridge construction. And in this bridge construction, fiber optic sensing cables were installed. And somehow not everyone was well informed enough about where those cables were. So when the formwork was removed, you can see here is that the lid of the connection boxes was ripped off, and also the connectors have been ripped off. Not such a big problem, just splicing new connectors solves the situation in this case. However, still something that could have been avoided. Another situation, here something is being added to a tunnel lining, and you can already see, okay, the drilling machine, and you have to be sure that whoever is doing some sort of drilling is aware of the fact that there are fiber optic cables and he's not just making his drilling holes there. We have tiny cables, but sometimes, bad luck, people just hit exactly that tiny little cable. Yeah, but if everything is taken into account, so if you select the right cable, the right reflective back reflection technologies, or Brignon radio or Raman, and you do the right documentation, you can really make a long-living permanent monitoring system of a concrete structure. And this is just a joint application that we made with our spin-off company ACI Monitoring. What we can see here is here we have two tunnel lines, and the red lines correspond to the location of the sensing cable. So we have it on the ceiling. We also have it then here in several cross sections. And I think what's important to notice, such a monitoring system is also a living thing. So at the beginning, you make an installation and you may just measure at the location where you have installed the fibers. But at a later stage, you can move to cross passages. So you don't have to access the tunnel tubes, just the cross passages. And also in this case, the fibers are connected to normal communication fibers, and everything is routed to a central measurement container. And currently, this measurement container is on the top of the construction site, so the top of the tunnel portal. And from here, measurements can be made without any interference of tunnel construction. When you think about other technology like total station measurements, here you're very often just in the way of the construction work with the tripod and instrument. Here we can make measurements, not just epoch-wise, but permanently all the time without any interference of the tunnel construction. And at the later stage, when the construction has been finished and the tunnel goes into operation, the location of the instrument will move to the operation room of the tunnel building. So also during the operation of the tunnel, there's no need to interfere with the traffic. And in such a setup, it's also possible then to convert it into a fully automatic alarming system and warning system with automatic report generation. And also then if thresholds values are exceeded, people are informed where to look and what happened there. So actually this brings me almost to the end of my talk. As initially said, we are talking about large concrete structures. And what we wanted to get across today is that fiber optic sensing is highly sensitive, and due to the distributed nature, structure deficits can be detected. So we know that something happened. We know where it has happened. So we can localize it. We can identify, was it bending? Was it yet just, or was it cracking? We can quantify it. And really important, we can do all of this at an early stage of the deficiency. And at this stage, repair is usually cheaper and the damages aren't that big. What I wanted also to get across is that fiber optic sensing in concrete is already beyond research. The cables are robust enough, and when you do it right, when you document it right, you have a monitoring system which is suitable for measuring the whole lifetime of a structure. Really important is that the monitoring itself does not interfere either with the construction, but also not with the operation of the structure. So you don't need any closure of traffic lanes or no closure of tunnels. For instance, with long railway tunnels, it's almost impossible to get the closure of a tunnel for inspection. With fiber optic sensing, you don't need that. And also specific, I think, for concrete structures is that on one side, you do have the short-term questions. So to see what's happening to the hydration of the concrete, to the curing of the concrete, during the activation, so when the load is the first time transferred from the surrounding to the structure, and also what's happening during load tests. So this is one focus area. And the second focus area is the long-term monitoring. What we see very often, what has been implemented just for short-term monitoring is also a valuable tool for long-term monitoring. So basically, you integrate the fibers that you used for the short-term monitoring into a long-term monitoring. And from this, you can build up condition-based maintenance and warning systems. As Mark already said, this is a webinar made by the technical committee. And I would really like to thank the whole technical committee, especially Professor Kenichi Soga from University of California, Berkeley, who contributed with some examples, Dr. Wieland Hill from NKT Photonics, Dr. Jen Rocher from Omnisense, and Wieland Hill from NKT Photonics. And basically, I'm Werner Lienhart from Graz University of Technology, and also we have in this area a new spin-off company, ACI Monitoring. So this concludes my webinar. Thank you very much for your interest.
Well, thank you very much. To ask a question, you can use the text box over on the right, and we'll pass that on. But I do have some already, and I wanted to ask, or the question that's asked is the splicing of strain sensing cables identical to the splicing for communications cable?
So basically, we use the same fiber in the core. So for the fiber itself, the splicing is the identical procedure. So you can usually use splicing equipment that is also used for telecommunication. However, the main difference is that you need some practical expertise, because we are dealing with a strain sensing cable, where the fiber is basically not meant to be separated from the different cable layers again. So it's really needs some training that you're able to remove those different layers without hurting the fiber itself. But as I said, this needs some training. After that, it's a normal process, the same as it is with the telecommunication cable.
And I think actually you may can clarify an important point another person asked, which is that about fiber optic cable installed in a tunnel being used for monitoring. Can it be used for communications as well?
Basically, the cable itself, or the fiber itself, is the same. However, very often those strain sensing cables don't really have many fibers inside. So if there's just one fiber inside, you can, at the same time, you just can do either strain sensing or telecommunication. If you have several fiber cores, you have a thicker cable, but then there are also fibers available which have rigid cores for strain sensing, which have also a loose cores, which are used for temperature sensing. And of course, you can also use one of those cores for telecommunication.
Next question is how can the accuracy be verified?
This is a question that is very often asked, because the point is we install something and how do we prove that it really works? As I'm at the university, we usually have quality verification at several layers. So first of all, we can make component testing. So this means that we just take the fiber or the instrument itself. So your usual example would be we stretch a fiber, a strain sensing fiber, and take a look at load cycles and see how the relation of the Brignon shift, for instance, and the actually applied strain looks like. Or another point is we have in our laboratory fibers stretched at a certain amount and monitor them for the long term in order to see if there are some creeping effects of the cables. So this is just the individual component without concrete. When we embed them in concrete, we can do things like load tests, where we also can apply different independent techniques. So for instance, for cracking, camera systems can be used to see cracks on the surface. We can also apply vibrating wire stages for measuring inside. When you derive the bending shape, so when we make the double integration, we can also use total station laser scanners or image-based techniques. And also, we also try to see, to come up with methods to verify the accuracy in the long term. And this could be, for instance, that you have setups like we do have for the water dam. Here also some sections are installed in stable rock. So we can also see, or we would have been able to detect creeping effects or some trends by having some reference reading which should be 0. And again, we can also use for bendings, we can use total station laser scanners, or very often, and it was also shown in one of the examples of the piles, you had some single dots where a point-wise comparison have been made with vibrating wire sensors.
Okay, the next one, you've talked about dams and tunnels, but how feasible is DFOS for old reinforced concrete buildings?
So we have issues in Austria where we have to attach fire protection plates to concrete surfaces. So with an existing surface, and it's been retrofitted with some fire protection plates. And here the question is now, how do you monitor now this concrete surface? So usually you would say use a camera-based technique, or you go there manually with a crack meter, but all of this is not possible anymore when you have a fire protection plate. So for these cases, it's possible to attach a fiber optic cable on the surface, and by doing so, you can also see then if cracks change or if new cracks occur. So we have some installations where we actually are doing that. Important is here the right preparation of the concrete surface so that the cable is really rigidly connected and the crack is not just caused because your adhesive is cracking. It should only give a signal if the concrete itself is cracking.
So along the same question, obviously we talked about transportation. The issue was about water, tunnels, sewer, tunnels as well. Have there been use cases for those types of projects?
What is exactly the question?
It was, we've described transportation tunnels, and the question is, what about water tunnels or sewer tunnels? Has there been experience for those?
So basically, at the moment, we're just preparing a project for that. So here, it's a question now if it's a newly built. If it's newly built, it doesn't really make much a difference if it's a water tunnel or if it's a railway or highway tunnel. You embed it basically in the tunnel lining directly. If you apply it on the surface, here's the question: how you protect the fiber when you have the material flowing by. So this is something that has to be worked out, especially when you have some aggressive chemicals that may work on the cables. Maybe just one question for the cables. There are at least 50 or 70 different types of cables just for strain sensing. So it's really about selecting the right type of cable for the specific application.
So this is probably a natural follow-up to that particular question, sort of anticipating the answer is, what type of cable works best, loose or tight buffer cable? And you may want to expand on that. Mm-hmm. So what are the, maybe phrase it slightly different, is sort of what are the considerations that you use in choosing from all those various options the kind of cable that you go with?
Mm-hmm. Okay. So for strain sensing, it definitely has to be a tight coupled cable, because otherwise you won't have that strain transfer. If it's acoustic sensing, it depends also on the amount of the impact, because if it's tightly coupled, this means every vibration is fully transferred to the core of the fiber. Maybe sometimes you don't want to have that in acoustic sensing, because sometimes then the signal is too strong to be caught by the acoustic sensing. For strain sensing, let's say if you do use brilliant, you have a signal that is sensitive to both temperature and strain. So usually we do have here a line where one side is tightly coupled. So this part is sensitive to temperature and strain, and the back line is loosely coupled. So this means in the back side, we're just sensitive to temperature. And if you make the spatial allocation right, you can basically take a look at the two different signals at the same physical location. So fiber length-wise, it may be totally different, but at the same physical location, you can then use the reading from the loose cable to compensate the temperature impact on the rigid cable.
So the next question is related to that, and that really, I think, dealing with the various different approaches of fiber optic sensing, which is to use different electronics to detect temperature, strain, and acoustics.
Yeah, that's one downside of fiber optics. The sensing element is usually rather cheap, but the interrogator has the costs. So for acoustic and strain sensing, it's different instruments. For temperature sensing, it's a question what effect you're going for. So if it's purely temperature sensing, it could be that you use a Raman instrument, and this usually uses multimode fibers because there you have a better signal to noise ratio. When you use Brilliant for strain and temperature sensing, then you can do it with the same instrument, but you need different cables.
And next, related to is what kind of spatial resolution can you achieve measuring strain to detect very small cracks?
I had it in that high resolution distributed strain sensing. So basically, in this case, it has to be a Rayleigh instrument, because with Brilliant instruments, usually in the range of a few decimeters of spatial resolution, which is not sufficient. For high resolution strain sensing, you usually use gauge lengths of 1 centimeter or even lower. And with that low, so just a few millimeters gauge length. So with that, you can really depict them small cracks already.
So now here's, frankly, a little bit of a softball question for you, but does long-term monitoring mean that we are measuring strains on a bridge or tunnel all the time, 24/7 for a couple of years? And if yes, does that really make sense regarding costs? So I'll let you.
So just to give you some background information, we are currently building 3 very long tunnels in Austria. So one is 27 kilometers long, the other one 33 kilometers, and the longest one is about 60 kilometers long. And exactly this question arises there. So to answer your question, no, it does not make sense to measure there all the time, because if this would have been needed, there would have been a wrong design of the tunnel. So the tunnel, however, if I'm going maybe back to that slide, however, this setup is very useful, because this setup, we are aiming for all the tunnel installations. So we're aiming for the fact that we can make measurements without entering the tunnel. And the idea is now that we make epoch-wise measurements. Everything is connected. However, the instrument just goes there maybe every half a year. So every half a year, we make a measurement of the whole length of the tunnel. But if one of these measurements does show some impact, then the instrument stays there and it switches now, or stays there, and now we switch to a permanent monitoring, maybe for, I don't know, 2-3 months, and see the closer detail how changes evolve over time. So usually you won't keep an instrument there running for 100 years permanently. You will have a permanent monitoring during the construction phase, then you switch to an epoch-wise monitoring every half a year, for instance, and in case you see something, you will then switch again to permanent monitoring. That's the approach that we follow at the moment for our long tunnels in Austria.
I think we're coming up to the top of the hour, so I'll cut you off there. Obviously, if folks have additional questions for you, we have both the contact information for the FOSA Technology Committee, but also for your email at the University of Graz. So thank you very much, Werner. For those who are interested in listening to this again, this webinar will be posted probably within the next 12 to 24 hours on the Fiber Optic Sensing YouTube channel, which is also hosts a variety of additional webinars as well. So thank you, and that concludes this webinar.